Hello, good afternoon. Thank you for having me and inviting me to join you today. It's a privilege and an honor to be here with all of you and the esteemed speakers and to meet everyone today. My name is Rania Khalaf. I'm the director of AI engineering in IBM Research AI, and I'm based out of Boston, Massachusetts. We're hearing a lot now about machine learning and about AI, and we see today that we are seeing a lot of really practical applications and implications of what machine learning is doing for us. And a lot of these are seeing real applications in business and in our daily lives, from language translation to speech recognition to face recognition and object detection. Now, AI is not new. Some of you may remember the 80s and the 90s when there was a lot of hype about AI taking over the world, and then the bubble burst, and we are seeing now a re-emergence of artificial intelligence again. And people wondered what has changed. Some of it is in the algorithms, in fact, but really a big part of it is that there is now enough data, enough labeled data, and there is strong enough and powerful enough compute to be able to do the calculations that are necessary for things like deep neural networks to be able to do the training in a finite amount of time and be able to inference fast enough for the kind of applications where they are needed. So the advent of things like GPUs and TPUs has allowed this type of compute capability to occur. We in IBM do a bit of the type of AI that maybe you are not seeing as closely. For example, there's a lot of AI in consumer technology, like in photographs and finding your friends and who's in a photo and things like this. But in IBM, we focus a lot on AI for the enterprise, AI for business. And this is applying into domains like healthcare, finance, and so on. And in these areas, what we see is quite important is that our clients may not have massive amounts of data to learn from, which some of these deep neural networks today require. Additionally, they are in fields that may be regulated, like healthcare or finance, where it's important to be able to explain why the answer is what it is. So if a neural network says to me that it is likely that the patient has cancer, I need as a doctor to be able to explain why. I cannot just say the computer told me, right? For the patient to understand me, but also from a legal point of view, I may need to be able to justify and provide the provenance of the algorithms. But a lot of these algorithms are black boxes, and the mathematics of them are not really clear on why they do what they do. So there is a scientific problem to solve, as well as one in understanding through visualization and so on. And we need to have multimodal ability, so that means different modalities at the same time, speech and images together, to solve for those together. In my team, we focus a lot on making it easy and delightful to build AI models and AI applications. This is a big problem because if you think about what it takes to create models and applications, you start by collecting data. There are already problems there. You need the data, you need to label it, you need to clean it. Then you have to build and train models. And if you have these massive models, then you need specialized hardware, and there are many languages to choose from. There are not the right abstractions. Once you've deployed your models, you need to inference with them either on the edge, on a mobile device, in the cloud. And then you want to put them into applications, because it's not the end goal is not to make a model. The end goal is to predict if something is going to happen or to determine if an image of an X-ray shows a particular disease. So once you build the applications, you need to then monitor and evolve the application, but also potentially your model might change. And the same model may be used in different applications. So this has been referred to as the AI engineering gap by the folks at Berkeley. And we see a lot of research in it in several locations. We in IBM are very active in this space, as well as the Berkeley RISE Lab, the Stanford Dawn Project, and others. This has led to a new conference. For those of you in academia, I would encourage you to look at it. The inaugural conference was last month in Stanford as a small one-day event, but there will be next year a major conference, a 3-day event in this space. So this is for research at the intersection of machine learning and systems. Why is it hard to build and deploy these machine learning models? It's hard at each of the 3 stages. When you are training it right now, people are often gathering from open source software, some stack, and building their own way of how they're going to train their models. They have not standardized on it. We see a lot of people with a GPU that they got a hold of on a machine in their lab, and they are rolling whatever software they can that makes sense. Once you deploy your model, the software engineering practices have not caught up with machine learning. So what does it mean to test something that is statistical properties? What does it mean to debug a black box model? And finally, once you are doing inferencing, you need to be able possibly to do real-time processing of these things and to move them around from edge to cloud and on-prem. So in order to tackle these problems, one of the first things we did was we created a deep learning service. This is a cloud-based service that we started in research some years back to help all of the folks in research and some of the teams in Watson to train their machine learning models that need GPUs in an as easy a way as possible, so that they just have to worry about their data and their models, and they don't have to worry about scale, about hardware, about networking, and so on. In creating this, we also use it as a vehicle to do research on many levels of the stack, all the way from new programming models down to advances in the cloud stack. In IBM, we also do research on the physics of AI, which is around new hardware for AI. But my team, we are mainly software folks, software guys and girls. So we'll look at next a few of the layers in the stack and some of the research involved and the challenges that we see. So first, we look at meta-learning. So meta-learning means learning to learn, in a way. And right now, if you want to train a neural network, it is very much an artisanal thing. There's a lot of iteration, you change different parameters, you try again until serendipitously it eventually will work and you'll land on just the right set of parameters. So this is a machine learning problem. You could learn you can find what is an optimal set, or you can find what is a near optimal set of parameters that you should use for a neural network. So we have research ongoing, and this is an active area around automated machine learning, an active area of research that is quite exciting about trying to make it as fast as possible for people and as painless as possible to create the optimal neural network architectures and the best hyperparameters for the problem at hand. Having moved on from, assume now you have your data and you have used this wonderful technique to help you create the best model that you can have, how can you now train effectively and efficiently at scale? So we are also doing very active work around distributed deep learning. And we have been able to show that we can scale the training to hundreds of GPUs and cut the training down significantly from many, many days to a few hours. And this is done by creating a new way of balancing communication and computation between the different nodes and doing so effectively. We mentioned earlier that one of the challenges in machine learning is to understand what the neural networks are doing and what your models are doing. One of the ways we are tackling this in my team is we have a lab, which is the Visual AI lab, where we have teams of visualization experts and machine learning experts that work together to create representations that are effective visual encodings to understand how these models are behaving and how people can understand them in the best way. So on one side here, we see a visual tool for understanding how LSTMs work. And on the other side, if you can also try this, if you go to formafluence.io, our researchers have basically taken the Google Quick Draw dataset, And they've done some very interesting analysis of it and some real-time, some animated graphics that you can see that overlay on each other how people from all around the world draw different concepts. So for people who don't know the Quick Draw dataset, this is a Google experiment that's available for anyone to try. And you try to, it tells you, ice cream, and you try to draw ice cream as quickly as possible. And so it tries to also guess what you are drawing. So what you're doing is try to understand how people represent concepts, compare them together, and we see like in some countries people draw ice cream only 1 scoop, and in some other countries always draw 3 scoops, and there are other really fun things we can see in this data set. The other thing is to try to also understand what the neural network is doing. As we said today, neural networks are black boxes. Like if you have a decision tree, you can kind of visualize what it's doing and where it's splitting. But if you have a neural network, you end up with a bunch of weights and a bunch of layers and the result, and you hope it's good. So one way, while some of the scientists in our teams are working on new kinds of models that are more interpretable, we are also in the Viz Lab, we are trying to create visualizations that help you understand the neural networks of today. So what this picture is showing is a 3D representation. And really it's, you can manipulate it, you can spin it around and highlight different things. But here it's using the open source fashion dataset, and you give it the picture on this side, on that side, of a shoe. And it's trying to figure out, in this case it knows this is a sandal that was shown in green. On the other side it has 10 possible categories that it can detect. And it knows that it's a sandal. And what the visualization lets you do is it lets you see the information flow through the network. So that is what the blue and red lines are showing, and the thickness of how much information is flowing. And you can see how the network is connected, what different layers are doing, what different neurons are doing. And one way we use this, for example, is we gave it 2 images that look kind of the same, but where the network thinks one is a sandal but the other is a handbag, even though they look very much the same. And for those of you who are familiar with deep learning, you must have heard of adversarial attacks. In this case, it is where you change only a few pixels in an image that are not visible to a human eye. You wouldn't really know that the images are different, but it is enough to trick the network into thinking it's some completely different thing. And they do this kind of by reverse engineering what the neural network is doing. So we show that if you give 2 pictures that look pretty much the same, that were generated through an adversarial attack, we can see what parts of the network are the ones that are responsible for this problem. So now we get to a topic that I think also is near and dear to our hearts here, which is around bias detection and model hardening, but really about bias detection. This is a very active topic for the community at large, and for IBM in particular. We have been doing quite some work on this, and here what we see is a description of an approach that we have done for removing bias in data by pre-processing the data set to remove bias in a way that still keeps the data in being meaningful. And this was presented at NIPS in December. And if you're interested in the papers there, also we have a nice blog post that explains how the work is doing. And you'll see that on one side, before we run the pre-processing, you can see that this is for loan, application for loan, and you can see that white people were much more likely to be approved for a loan. But after we do the processing to remove race from in the appropriate manner from the data, then we see that the data becomes much more, the model then is much more fair. One thing we have done also is we are very interested in how people understand the research that we do and interact with it. So we have created this URL over there, an interactive application for anybody can go and try to play with the data, and they can, it's an experiment to see how people understand bias and understand models. So we've used this approach to visualize an interactive experiment where you can play around and you can see how you understand if the data is biased or not and whether the model is helping it to debias. And we had deployed this demo on iPads and NIPS, and we had many people try it out and at several other conferences. And we've collected data from it, and now we have submitted a paper on that research, basically, on how people interact with the bias data to Kai. As I mentioned, we at IBM are very conscientious about the issues of bias and fairness in AI. We are a founding member of the Partnership for AI, whose mission really is to develop and share the best practices for using and developing AI technologies. We also were, I don't know if some of you have heard, I didn't have time to get the slide in, but I thought it would be interesting for today. But there was a study out of MIT by a lady called Joy, who did, she has a parliamentary data set, if any of you are interested in doing research on bias, that she took pictures of people from parliament in different countries, and then she compared the visual recognition, face recognition services from the major vendors, and she found that most of them are very bad at detecting black women in particular. And she contacted all the companies that were in the study before she published it. And we were very proud in IBM. We managed to respond to her and to update our service to beat all the other results and do like significantly better on this in a very, very short amount of time. So we're not very proud that we didn't have good results in the beginning, but we are very proud that we were able to quickly react to this. And that is what we will see, I think, in AI, that as new data sets emerge and new benchmarks emerge or new kinds of attacks emerge, we will have to keep improving the platforms that we have to continuously check for these and be as best as we can at improving our systems and keeping up to date and ahead of these things. Finally, we moved to having talked for a while about models and how you create them and how you could attack them and how you debias them. Now we'll spend just a few minutes to talk about applications of AI. So in this case, we are talking about chatbots. And here what we did was, chatbots use different models, but it is its own application. In this case, it is an application that's an agent. Like if you go to some website, sometimes it tells you to talk to an agent and you can kind of text chat with a thing, and that's often not a human. Although sometimes I ask, like, I was on with my cable company and I'm like, are you a human? And it wasn't clear, yeah, I had to really test it, Turing test. But so we have this chatbot of a customer that uses our IBM systems, and we were working with them to see if we can use machine learning to improve the model, right? So again, this is kind of AI to improve AI. So you can say, and we call it Watson trains Watson in the lab, right? We just say, that's what we are trying to do. So you have a deployed AI system, and it's generating logs. Can we take those logs and use them to figure out how to improve the training so that when you can retrain and continuously improve your service from these logs? Here's one example where this was a chatbot that was deployed to a customer where the accuracy was great. Like the model looked fantastic, but the chatbot was not doing well. People didn't like it at all. And it was very confusing because what you measure is accuracy and you don't know why people don't like it. So we did some analytic on the chatbot logs to detect egregious conversations, which are bad conversations, to try to understand why the chatbot is behaving that way. And the idea is that then if you can detect them, can you prevent them or react better? If you see the conversation going like this, can you switch to a human right away, for example, right? And this is a paper at the NAACL 2018, the PDF already in archive, people are interested to read about it. So, what is next for AI for AI? So far we have talked about, why it's hard to build models. People talk a lot about AI and they talk about algorithms and they talk about hardware and they forget that in between there is real people who have to build applications in a repeatable way that can scale, that, if your top developer leaves, that a new one comes, that person can take over the code, and so on. So that is what we focus a lot on, which is this platforms and patterns and programming models and abstractions for AI. And how to do things like check for bias and security in a repeatable way. Assuming all that works perfectly, then We are now building AI applications and models, and it is really, I mean, some people are asking me, are we at a point our computers are going to take away all our jobs and they're going to write our code? And no, we know we're not even close to that. So I think there's a lot of exciting things ahead of us, though, and we're at the beginning of an exciting journey. So with that, I thank you very much. I put here behind me some thoughts of IBM's commitment to diversity. We are really very proud of our history in this at IBM, and thank you very much.
Thank you, Rania. This was really very insightful. So we'd like to open the floor for questions. So we have a Q&A session now. So please, anybody has a question for Rania?
Yes. So what we have done now is we do some analytics on the logs so that we have built a model to detect bad conversations from good conversations. And the idea is that then you can, well, one is you can try to use it then to improve the model altogether. But then what we would like to do is to see if we can use it so that if you're detecting, can you detect in real time that the conversation is starting to go badly, and then transfer it to a human, right? So just stop the bot, get it out, because you would lose the customer. Eventually you want the customer to buy or not leave or do something, right? So. It's many different things. It could not be engaging with the person or just missing the point of what they wanted or giving them the wrong answer. Mm-hmm.
Sorry, how do you define a bad conversation? I mean, it's sometimes relative. And
yeah.
It's not always bad for you as the same for me. So how are you able to put the criteria for it?
So one of the criteria was if people leave, like they quit the conversation, right? They stop engaging. Another criteria you could look at is whether sometimes, when they're done also they could say how it went, but then we wanted to analyze to see if there were indicators ahead in the chat transcript. But you can also see the paper. I don't know if they're going to share the slides later because the links are hard to remember. But you can also read about it. And that work is quite early stage because I think it is very hard to do it extremely well, right? But I think there are many things you can do along the way, and this is the start of being able to detect that. They can do. Some people have done sentiment analysis, for example, on the quality of the conversation and things like this.
Hi, thank you for this interesting presentation. When you are talking about machine learning and AI, is it a dynamic machine learning and AI or static? What I mean is static, when you have a data, you clean it, you train it, you implement it after testing. But dynamic is when you learn from every new data point. So you have like a live training on each new data set. Which one we are talking here?
I think the talk so far could apply to both. I think most of the work historically has been on the more static way, but active learning or online learning is a very big area of research. And now there are ways to close the loop, but knowing exactly when you retrain or when you have enough data that you should train or how much your model has strayed away from what you had trained it on that you need to find a different one or make a new one is an active area of research.
Any other question? I have a question, actually. So this is very interesting. So you're making it more accessible, more reachable to build these AI pipelines. So I would believe your customer is a researcher, is a scientist, or are you making it more accessible for everyone to be able to build these models?
We had a lot of discussion on this, actually. I think we're starting with data scientists and developers and software engineers to make their lives better. We do have some work for helping end users that takes advantage of this. For example, the Watson visual recognition service that we have this thing called custom models. So you can just bring your data and behind the scenes, it has a base model trained on tons of data. You bring in your data and it'll retrain with that and specialize to it. We call it uses transfer learning. So then you have created a new model for your data and you don't know anything about machine learning or data science. So we do a little bit of that, but my main focus now is on the software engineers and data scientists, because if we see how they are working today, there's a lot of stuff that it's very homebrew and it needs a lot more tools and help, right?
Yeah, I completely agree. So thank you for that.
Thank you.
Yes, my question, in fact, I'm going to tell you something and you're going to correct me, okay? Because I would like to know your opinion on that. My concern is about the terminology of artificial intelligence. Honestly, I see no intelligence in artificial intelligence. Why? Because intelligence is finding out new solutions. Smartness is doing solutions properly and correctly. Now all these technologies, starting from machine learning, which is old like 100 years, which was rebranded, okay? And data scientists who are data analysts were rebranded data scientists. Artificial intelligence, isn't it like smart coding only? Because any software, we talk about artificial intelligence, if you give them anything outside what they are programmed to, they are not smart enough to be intelligent. So why do we call them artificial intelligence at the time there is no intelligence?
I think there's many ways to answer this question. One way, we will pull the audience. No, I'm kidding.
This question is debatable.
Yeah,
it's for everyone.
It is.
I talked many times. I talked with SaaS people, okay, and they never have an answer.
No, I'll tell you a few things. Well, someone was telling me when I was at this conference in February that the big joke is that it's AI to venture capitalists and machine learning to everyone else. but I think so. It's AI if you're trying to raise money. No, but that's the inside. That's the inside joke. I think that in effect it is pattern recognition. It is really good pattern recognition with huge amounts of data that is now better than what we can computationally compute. Is it smarter than your 1-year-old kid, right, at certain things, or does it learn the same way? That is a very active area of intelligence, of research now around neuroscience and machine learning. If you see, I was at the launch of the MIT Intelligence Quest last week in Cambridge, where they were really bringing together neuroscientists, child psychologists, and computer engineers and computer scientists to start to continue to look at how do you build effective AI and machines that learn and understand. I think from the point of view of building machines that learn, I believe that machine learning is doing that because you build a model and you continue to improve it over time and it learns from the data it sees. Does it know things it has never seen? No. There is no magic, right? There's no like razzle dazzle. This is, at the end it's bits and data that you have that you're going to learn from. And we are a long way away from AI that is going to achieve the dream of the nightmare or the dream, depending, taking everyone's jobs away.
Hello, I just wanted to ask about machine learning platforms. Assuming that in machine learning, algorithms would deduce information after you feed them information, is the initial data set actually important in a sense that what you feed it initially will determine the overall path it's heading towards? If so, how do you exactly determine what you should feed it, initially when it's first developed?
That is an interesting problem, especially for if you want to be learning continuously. I think right now it's going to depend on what you are trying to learn, and honestly, a lot of it is also going to depend on what data you can get your hands on. Especially if you're in an academic institution. We were just discussing with Dr. Mariette about this specific problem. But I think the model will only be as good as the data it has seen. So it's very important to start with as data that is as representative as you think you can get your hands on for the problem you are trying to solve. But we have models like, we train our base visual recognition model on ImageNet and other things, and that has pictures of, a moose and a car and a person, anything. It has pictures of everything. And a customer might buy that to do like car insurance, something or other. So then we specialize it for pictures of cars as well. But the model was trained on other things too. So that's, it works because it gives you a base model, like a base understanding of pictures that you can then specialize from. Thank you.